So we are at multiple linear regression. It took all quarter to get to the best part, and we only get to spend a day on it. So hopefully we can do it some justice. Again, I'm like usual. I'll try not to dig too deep into this. I mean, it's just we only have a day, so. But we'll talk about fitting and interpreting a multiple regression model, evaluating multiple regression models, categorical predictors with several levels, inference for the multiple regression model, interaction, and model selection. In practical settings, there's probably more than one thing explaining these phenomena that we're interested in. You know, you might have been looking at one of the examples or some of the homework and thinking, well, that definitely is only part of the picture. And actually, that's a problem for regression. If you have a non-fully specified model, but for the sake of teaching, it's okay. But if you're actually doing research, you got to make sure that you fully specify your model, meaning that you account for everything. Otherwise, you're subject to different kinds of bias. Yeah, so this is a multiple linear regression model is used to estimate a linear relationship between a response variable y and several predictors, x1 through xp, or in different nomenclature, xk. Statistical model is y equals b naught plus b1, x1, so on. B naught again is our intercept term, and all the rest of them are slope terms. So there's several applications of multiple regression. We're going to talk mostly about estimating an association between a response variable and a primary predictor of interest, while controlling for or adjusting for potential confounding variables. So maybe you want to predict house price, and you have one main thing being square footage that you think drives it, but then you've got a lot of other things they're not confounding variables in the case of a hedonic analysis on houses, but they would be much smaller than square footage probably. Or different things like that. If you're wanting to control for all of the sources of variance that you can find. In constructing a model that effectively explains the observed variation of the response variables. That's what we're trying to do. Just trying to account for the variation we see. So there are, and you've probably caught me slipping up. I've tried to be really consistent on my verbiage, but one of the reasons that it's difficult is because there actually are several different things that people call these things. I mean, they really all mean the same thing. So y could be our dependent variable. It could be the explained variable. It could be the response variable, the predicted variable, or the regressand. The x's could be your independent variables or your explanatory variables, your control variables, your predictor variables, or your regressors. They're usually kind of paired. I mean, explained and explanatory, response and control, predicted, predictor, dependent, independent, and less so at the regressand regressors. But they're just different terms for basically the same thing. Some of them make more sense in certain environments, but depending on the nature of what you're doing. The other thing that I've mentioned, but I wanted to make sure that we covered, was that you can do log transformations on variables, and that will change the interpretation of each of the variables. And I have examples for all of these. You could have a level, meaning that the y equals b naught plus b1x, there's no log in that, no log transformation of either variable. You could do a log transformation of the x variable. You could do a log transformation of just the y variable, or you could do a log transformation of both the x and the y. And each of these different functional forms has a little different interpretation. So what we've been doing so far has been the level, meaning that a B1 change in X leads to a, well, it's easier to think of it as a 1% or 1 unit change in X leads to a B1 unit change in Y. If you log the independent variable, but not the dependent variable, you have a 1% change leads to a B1 unit change in Y. And on the log level, so the log of your dependent and level on your independent variable, is a 1 unit change in X leads to a beta 1% change in Y. And in the case of where you have a log transformation of both the X and the Y, you have a 1 unit change in, or 1% change in X leads to a beta % change in Y. So that'd be your elasticities in econ. They're measured with that. So percent change in this leads to a B1% change in that. So I'll have examples of each of these in just a bit. Fitting and interpreting a multiple regression model. Okay, so the example here is that statins are a class of drugs widely used to lower cholesterol. If followed, recent guidelines for prescribing statins would lead to statin use in almost half of Americans between 40 and 75 years of age, and nearly all men over 60. A few small studies have suggested that statins may be associated with lower cognitive ability. And there's a study here that collected data on statin use as well as other factors. And, so maybe we have the score of this test that has something to do with cognitive ability. And you have the age along the bottom. And I think in the last class, we had a model where we were explaining the score with age. So there was a certain amount of change in age led to a certain change in score. And of course, that was like, okay, so people's cognitive ability does generally decline as they get older. But, this doesn't seem like it's all that, it seems like there's more in play here. So in this case, they've added statin use, and probably that's what they're of interest of, what's of interest anyway. So they have this, they've added red dots to represent statin users and blue dots for non-statin users. And, if you're looking at this, you're probably seeing kind of a trend downward, which we already expected. Like I said, cognitive ability tends to decline. But what do we think about the red dots? I mean, it's really hard to tell, especially just looking at this. Clearly, as you go on, more people are on statins, and a greater proportion of the respondents here are on statins. So this is going to be hard to kind of piece out, like just visually. So thankfully we have better tools than that. But we can parse this out like this and see that, okay, so there might be a difference. If we were just looking at non-users versus users and their scores. So the users might be a little lower on their scores, but you got to remember that more people who are older, or the users, are an older bunch than the non-users, basically. So there's something confounding there. It's hard, so we need to piece that out. And if you were to just run a linear regression, single linear regression model, that would have statin user as a 1 and 0 if not. So you would have this your y equaling, and basically that would be the score, this FFT score, and that would equal an intercept and then a binary variables or dummy variable for statin users. And if you happen to be if you're looking at someone who is a statin user, you're going to expect them to score 10 points less, roughly, on this score. So the mean would be something like 70, and the statin users would be 10 points less. Okay, so that's one thing, and that's basically what we saw in this picture. But again, we have not dealt with the age problem. They are getting older as more of them use statins. So we might not have a complete picture here, is what I'm trying to say. So with the statistical model where we have multiple predictors, the coefficient of J of a predictor xj is the predicted mean change in y corresponding to a 1-unit change in xj when all of the other predictors remain constant. So let's see here. Now, if we add age is now negative 1.27, and our intercept is much higher. And our statin user there is a plus 0.8509. Oh, okay, so what's going on here? Well, as I mentioned, we know that people's cognitive ability generally declines. So we see that in the age slope variable. So if there's the age of the person, a bigger age, 1 unit increase in age leads to a 1.271 unit decrease in score. So we have the decline in cognitive ability that we would expect, but now we have this, we're controlling for more factors. We have this statin user variable. And that's saying that it's 0.8509 increase. So all else equal, the statin user has a higher score than the non-statin user. Okay, that's interesting. Is it significant? And we know if we go through and we look at these p-values, yeah, they all are. You could, if your alpha was 0.1, then statin user would be. Otherwise, if your alpha is 0.5, then statin user wouldn't be. But otherwise, you got 34 zeros on the other, on the next to that 1, and 99 zeros over here in front of that 4. So clearly, those are very small numbers. Just that the p-value on statin users is not that great, but it is probably sufficient for showing something. Okay, so here I have some more examples where we can take into account all of these different kinds of functional form. What you probably ought to be fairly comfortable with is this is the linear or the level. So in this case, it's college GPA is equal to 1.29 plus 4.53 times the high school GPA plus 0.0094 times the ACT score. We would expect that a 1 unit change in increase in ACT score leads to a very small change in GPA. A 1 unit increase in high school GPA implies a 0.453 increase in college GPA. So that one's should be pretty comfortable with that. What might be a little less, a little more, but just so that you know that these things can exist. If we did a log transformation of the wage, so say we were trying to explain wage, and we did that, took the natural log of each of the values of the wages that we have, and then we used that natural log of the wage as our dependent variable, we could have this regression estimated, where we have wage is equal to 0.284 plus 0.092 education plus 0.0041 experience plus 0.022 tenure. And that would mean that a 1 unit increase in experience leads to a 0.41% change in wage. Just go back to that little table I had and plug that in, get your answer. Math, I'm not sure what this was. It's some sort of math score for high school students. If this is a linear or a level, and we happen to take a log of our independent variables, then a 1% increase in staff size for this one implies a 3.98 unit change in math scores. So percent sticks over here with this log transform side. And then finally, you could have a log-log model where you were trying to maybe estimate your crime on a college campus. So, and you think it's a function of enrollment. So the bigger college has more crime. Kind of a statement there. But anyway, so that would be a 1% increase in enrollment here leads to a 1.27% increase in crime. So that is a lot of different ways of dealing with things. Now you notice that if we got a percent change in either or both the independent or dependent variables, that means we can now have curvature, doesn't it? We don't have to have straight lines anymore. Because a percent change is going to be different. So a 1% change of 90 is bigger than a 1% change of 10. So now we can have stuff that has kind of a curvature to it. And we're actually going to have more ways of dealing with the curvature. Because if you recall from the last lab, we had some of those diagrams that showed we could have had a pretty tight fit around a line, but the line had a curve. And now we're starting to develop tools that we can use to develop that. So we're going to talk about evaluating multiple regression models. Now, similar to linear regression, we have to have a handful of things before these models are valid for inference. We have, for each predictor variable X, the change of the predictor is linearly related to the change in the response variable when all other predictors is held constant. Again, we're going to be able to relax that some, but basically it needs to be fit. What you're doing needs to be fit for the models, that assumption saying. Constant variability, the residuals need to have approximately constant variance, meaning that you don't want to have your residuals remember, your residuals are the distance between the line that you're plotting and your observations, so your actual observations. And some of the plots that we've had maybe a narrower group of plotted points on one end than the other. And that's a problem under this assumption. You want the distance between those plots or those plotted points to be the same or approximately the same, regardless of the value of the regressor. So regardless of the value of this X variable, it needs to be roughly the same across those values. We need to have independent observations, meaning that each set of observations is independent. We don't want to have your observation affecting my observation and so on. We need to have normality of the residuals. So again, I know we're talking about the residuals a lot, but it matters. We want to make sure that we need our residuals to be approximately normally distributed, meaning that most of them are pretty close to that line and some are not normally distributed though. So it's not possible to make a scatter plot of a response against several simultaneous predictors. I mean, if you can think above 3 dimensions, you're an alien, I guess. It's really kind of outside of human conception. Because if you have 3 exactly, you're plotting in a 3-dimensional space, or if you have 2 variables, you're plotting in a 3-dimensional space. Anything higher than that, you're in a hyperplane, and it gets really hard to imagine pretty quick. So we tend to plot these things so that they are one y and one x. So you have your independent variable and your dependent variable, and you plot one against the other. Even if you have multiple independent variables, you just plot them one at a time. And then these patterns that sometimes develop are indicative of nonlinearity or something worse, or sometimes you'll have other things. But so we need, again, these normality of the residuals, and then the constant variability. We can assess that with plots as well. Have any plots? Okay, I don't have any plots. It looks the same as the single linear regression. I know I've probably broken the record of if you can do one, you can do multiples. But if you can do one, you can do multiples. One of the things that does change, though, as you add multiple explanatory variables, is that as variables are added, R squared is going to increase. So does that mean your model is better? So I added a variable. I'm trying to explain tree height, and I added a variable that was something that's completely unrelated to tree height. Something completely unrelated to tree height. R squared is still going to increase. Maybe minutely. It might be the sort of thing where the software is going to round it and you're not going to see the difference, but it went up ever such a small amount. But you did not improve your model by adding that variable. You're not controlling for any additional variance or any additional unknown variance. You're just throwing variables at it. And that's generally a bad practice. So in this case, we have this statin use and age linear regression model. And we have the R squared. R squared here is 0.285. And that's not great. It's not the worst thing in the world I've ever seen. but that means that you're only accounting for 28.5% of the variance you're observing in your Y variable with your X variables. So you've got the majority of the variance that you're not controlling for, which is a problem if you're trying to explain something. So we have and like I said, you could add a variable and it would get, that number might get ever so slightly bigger, but it would get a little bit bigger. If you add a good variable, it might get a lot bigger. So we have another tool. It's adjusted R squared. So the adjusted R squared is typically what we use to measure multiple linear regression as far as how much our variables are adding. Unfortunately, the R squared adjusted doesn't have an interpretation like R squared does. So R squared, you're saying, man, 28.5%. That's how much of the variance we're accounting for. And now with adjusted R squared, we have a very similar number of 0.282, but we don't have an interpretation like that. All we can really do is compare that to other models. Say, oh, well, this one's worse than that one, or this one's better than that one. As far as fit goes, it doesn't necessarily mean. Does that kind of make sense? Mostly important here is to understand that R squared, first of all, understanding the interpretation of R squared is important. And then understanding that there is a reason to have adjusted R squared, and then it's a point of comparison between models. But we don't, unfortunately, with adjusted R squared, you don't have the cool interpretation of, we're explaining a certain percentage of variance. Okay, categorical predictors with several levels. So back to this statin model here, with a binary variable, it's basically a difference in means. So the statin user has a score that's 10 points less than average, or than non-users, I should say. Okay, so that's one binary variable with only the two levels. What about more than two levels? So sometimes maybe you want to explain something with education. So you might categorize how high of education that this person received this part of it. So maybe that has something to do with their cognition or their ability to perform on this test, because they went higher in school anyway. So hopefully y'all are increasing in ability to do things while you're here. That's the goal, hopefully. And then here we have 0 for primary school, 1 for lower secondary, 2 for secondary higher education, and 3 for university education. So those will be our values. And if you're not careful, you can take the wrong direction on this. Do you suppose it's true that you're going to have twice as high of a score if you had high school than lower secondary school, higher secondary versus lower secondary? If you go from 1 to 2? Okay, so that's possible. I would buy that. But how did we decide on 1 to 2? That sounds arbitrary. So how we actually deal with these is we create a series of dummies. So rather than actually being able to regress and have an equation that is, we're going to have 4 different levels of education, and we will include 3 of them in our regression model, and that'll leave the last one as a base. Okay. So here we have these education levels. So the primary school education level, the scores are here. The whatever the next level was, the scores are here. The next level, the scores are here. The next level, the scores are here. And you kind of see an upward trend, as you would expect. You know, you more schooling than, or you are able to continue in school because you could. It could also be a selection thing rather than, you know, or it could be inheritability. It could be a lot of things. But in any case, scores generally increase with schooling. Now, the way we would calculate, we can calculate our means, and we say that our group mean for primary school is 40.94. Our group mean for those with slower secondary is 55.71975. The higher secondary is 73.07, and university is 85.905. Okay, so those are the means for each of those groups of education. Maybe what we should be doing now, if we wanted to have a linear model, we could fit that so that we have our intercept. Okay, that's our lower mean. And what we're going to do is leave out the primary. We're going to say our primary is our base. So whenever you have multiple dummies like this, when they're all basically of the same question. So in the case of each observation is only going to have a 1 in one of these. They could have a 1 in primary, in which case these are all zeros, and then that ends up with the mean of, or a predicted score of 40, which is primary. You could have if somebody had a lower secondary education, there would be a 1 in this data point or this row, and that would mean that they're going to have a 40.94 plus 14.77 mean score, or 55.71. They could have higher secondary. So maybe another observation has a 1 in this column and zeros in this column. Okay, so that means that this education level has a 32.13 unit score higher than this base group, which is the primary. And we look down here and we see that 32 points a bit higher. And finally, the university education, you're going to have 1 or whatever, however many observations, they'll have a 1 in this line here, or this box here. And that's 45.96. So basically 45 units higher than primary. And we see that there. We have 85 for our group means of these different education levels. So I'm trying to figure it out. Okay, so if we were trying to predict somebody's score and we had this would be the score here, and we had this, we evaluated this equation. So now we're looking at this, we see that the intercept is 40.94. And then the rest of these are all dummy variables. So somebody does or does not have the highest level of education. I know that, hang on, I'll finish what I was saying, then I'll come back again because it's not very well formed. The highest level of education for somebody is or is not this lower secondary education level. So somebody could, if somebody has a higher one, say higher secondary or whatever, higher second level, that means there is 0 here. So you might have, you're going to have somebody with a 0. Zero. So these could be lines out of the data set from this. And you have this, in this case, in this first row here, this would be an individual whose highest level of education was this secondary level. And their score would be 32 points higher than the primary group, the base group. And the base group is this primary level of education. And that's wrapped up in the intercept here. Then the next row here has a 1 in second, the lower secondary. And that individual, that was the highest level of education they had. And their mean score is 14 points higher than this primary group right here. And then this last row would be somebody who had a university education. And their score is going to be 44 points higher, 45 points higher than this base level of 40. So they end up with 85.9 now. So that is one way of looking at it. And this is another way of explaining this. Basically, the sample mean for all, for individuals who had primary schools, their highest level was 40.94. And then you have these increases for each successive layer or level of education. Okay. Now, inference for the multiple regression model. Again, our coefficients in multiple regression model, B0, B1, and so on, are estimates of the population parameters of the model. Y equals beta naught plus beta 1 x1 through beta p xp plus epsilon for the errors, where the errors are normally distributed mean 0, standard deviation sigma. The inference is normally conducted around the slope parameters. So your beta 1, beta 2, your question would be, is beta 1 or beta 2 actually different than 0? So does this education level lead to a change in scores or not? So here we have I have a null hypothesis where the beta variable, we say, okay, is the beta variable equal to 0? That's our null, meaning that there's no association, or alternatively, that it's not equal to 0, that there is an association between the x and y variable. The t statistic that you're going to calculate here has degrees of freedom of n minus p minus 1, where n is the number of observations and n is the number of predictors in the variables. I don't know why they don't just stick with K. And we might calculate a 95% confidence interval for the slope. So that you have a BK plus or minus the same as we've been doing for these confidence intervals, T star times the standard error. And only in this case, the T distribution with n minus p minus 1 degrees of freedom and the right number, the right sized area on the right. The F statistic is, back to this right quick. These are the same as the other T tests you've been doing. So if the T is big enough, then you're going to have a P value that's small enough to say, yes, there is a relationship there. So we can reject H naught and say that BK has some impact or has the impact we see there. Or we might have to fail to reject, in which case we just, if the T is too small or so on. The F statistic is an evaluation of the entire model. So the F statistic, the null hypothesis is that all of the betas are 0, meaning that not a single one of them has any sort of association. So the entire model is without use, really. If we have, though, you do the F test and you find out that the p-value is small enough, then you have sufficient evidence to reject H naught and the p-value and to reject the null and say that at least one of the coefficients is not 0. You don't really have, with the F, you don't have an answer on which one. Do you have a question? No, okay. I do that too. Just trying to get enough high enough blood. Like if I want some of my blood to go to my brain, wasting it in my arm. That's okay. So the F statistic and its p-value, they're like most of the things. They're on the P. They're put out from the software. The software calculates it for you, and you don't have to worry about it. You just have to interpret it. So here is a regression output where you're looking at score versus just the education level. And here you have, looks like all of them are going to be alpha, they're going to be significant to the 0. They're very significant. And here's your F test. That's a large F value, and our p-value is very small. So yeah, the model, at least one of the variables is not equal to 0, or one of the slope coefficients is not equal to 0. And in this case, actually, all 3 of them are with the t-tests are not equal to 0. Now, you might do the same thing with ANOVA. So for pairwise connections, it's not that big of a deal. Maybe we reanalyze this again, and we control for a lot more. So we have statin, we have the age of the person, we have education level, and we have CVD. I don't remember what CVD is. Anyway, we have, are they a statin user? And then we have this slope coefficient of 4.69. So you would expect statin users to have a score that was 4.69 points higher than the base group. You would expect, you have your age right here. You would expect that an additional unit of age would lead to a 0.92 unit decline of scores. You would have a Education, the lower second level, these are all relative to that base unit of primary education. So it's going to be 10 points higher or 21 points higher or 33 points higher, depending on what level of education they have. And I still don't know what CVD is, but apparently if it's present, it's 7.56 points lower, you would expect. These are all significant to at least the alpha equals 0.10 level. So not really all that. I mean, alpha equals 0.10 is often used, but more frequently, alpha equals 0.05 is used. So we might not actually consider this statin user to be an important variable. We might say that if we had set our alpha at 0.05, we would say that there's insufficient evidence to reject the null. We would say that our statin user variable is not significant. Could happen, depending on whatever you set that up to. Okay. The next piece we have is that sometimes things have multiple effects, or maybe you have a multiple regression model where, in this case, we just have our normal regression model. And that assumes that, if you have an explanatory variable that changes by 1 unit, then the predicted response changes by beta J, regardless of the values of all the others. If we have an interaction, that's not necessarily true, though. Maybe we could have an interaction where one of the predictors is categorical and the other is numerical. So, for instance, maybe this model here does total cholesterol, and it's equal to beta naught plus beta 1 age plus beta 2 diabetes. So we would expect that total cholesterol has something to do with age. Okay, and we have diabetes here. Diabetes is a dummy variable, so you either have it or you don't. So it's going to be a diabetes being true. So if someone has diabetes, we would expect their cholesterol to be 0.317 units less than whatever this is measured in. Total cholesterol versus age and diabetes. But it could be that diabetes and age are related in some way. So maybe diabetes hits people that are older harder as far as the cholesterol goes. So then we would need an interaction variable. So in this case, we have this, the model for diabetics is red and the one that's for non-diabetics is blue. Our slopes are the same, as you see, because we only have a change in intercept with this variable here. We had this change in intercept, and okay, but the lines are parallel. What if they're not? What if, for some reason, you were to fit these separately? You would find that cholesterol versus age in diabetics, the line is actually downward sloping, and cholesterol versus age in non-diabetics, the line is actually upward sloping. So we might actually have the wrong coefficient on our slope entirely. It's the sign. So maybe it ought to look more like that. But you get there with an interaction effect. So we're going to need to have an interaction on diabetes times age. So we're going to have a dummy variable of diabetes again, and it's going to be multiplied by our age variable. So this slope will only change for those with diabetes. So we have, in this case, we have our intercept of 4.69. Our age is 0.009. And so we would expect that an increase of 0.009 points or whatever this is for cholesterol for a unit of age. We would expect that diabetes increases cholesterol by 1.718. And we would expect that it actually is the effect for diabetics is muted by the diabetes. So it's going to make this slope smaller. In fact, negative. Interesting. So if we were to evaluate this for diabetics, the model equation is, say, it'd be diabetics equals 1, 4.70 times this slope coefficient for the age plus 1.72 times 1 for diabetic minus 0.034 age times 1 for being diabetic. So then if we simplify this down, you end up with 6.42 minus 0.24 times age. That's our equation for diabetics. And for non-diabetics, the diabetics yes is equal to 0. So these two terms fall out entirely. So all you have left is the 4.70 plus 0.0096 times age. Okay. And we determine whether or not it's significant in the same way. We come over here, we look at the p-value, and it's significant to any realistic level of alpha that you might choose. So there is an effect that it's different than 0 for the interaction between age and diabetes. Okay, so how do you go about selecting variable or models? There's actually some controversy over this. You could throw everything in, and that would not be a desirable thing to do, though. You need to have a model that explains as much variation as possible in your response variable with as few predictors as possible. So there are ways that you can choose your model. So if you have 4 different ways of measuring education, but we don't want all of them in there. You need to pick a way to measure education. If you have, if you're even wondering whether or not to include education, it's a point of discussion on whether or not you should include it, even if it's insignificant. I would say you should. You need to include it. If it's theoretically important, it needs to be included in the model. So how do you go about doing this? You explore your data first off, examine your distributions of individual variables and relationships, and you do some initial model fitting. So you run your regressions a few different ways. You look at that, and you're going to work towards a model with the highest adjusted R squared, assuming that you are including all of the things that you think are important theoretically. This is where you can get in trouble if you just select models based off of R squared or adjusted R squared. It can. Now I got thumped on the head really hard in my thesis for my master's degree defense, because of the way I told the story about selecting variables for my regression. That was it was not appreciated. So that's it's important to tell your story accurately, but also to not select based solely on that. You need to have a theoretical construct for why you're including the variables, and include the variables because there is a theoretical construct for you to use it. Without the theoretical construct, the model doesn't mean anything anyway. It just says that there's some sort of mathematical connection. So that is multiple linear regression. Okay, so this is not due till, I guess, Sunday night, but I think if I were you, I would go ahead and get it done. It's not very long. I think. '15th. Is that Sunday night? Okay. But I mean, it's only that long. So I think I would go ahead and do it if I was you. Okay, so here we got the first question. Timber yield is approximately equal to the volume of a tree. However, this value is difficult to measure without first cutting the tree down. Instead, other variables such as height and diameter may be used to predict a tree's volume and yield. Researchers wanting to understand the relationship between these variables and black cherry trees collected data from 31 such trees in Allegheny National Forest, Pennsylvania. Height is measured in feet, diameter in inches at 54 inches above the ground, and volume in cubic feet. So here we have our regression model. We have our estimates of our beta coefficients. So our B's are in this column. Standard errors right here. The t-value is right here. So for a t-test, and these are the p-values for determining significance of those. So we write the regression model. We need to start with our intercept, negative 57.99 times 0.34 for the times height, and plus 4.71 diameter. So that is the model. That makes sense? Okay. Definitely will be questions on this on the exam. So I mean, this is what I think is the most important thing we're doing. Which one? This one right here? Minus 57.99. So it'd be this right here. Okay, keeping the diameter constant, how much additional volume should we expect from an average tree if height is increased by 1 foot? Okay, so here is our coefficient. Here I know what I need to do. Here's our height coefficient. What do we think? If we increase height by 1 foot, what's going to happen to our volume? Going to go up by 3.4. Yeah. Goes up by 0.34. 1 unit change in X leads to a B unit change in Y. Okay. Are each of the predictors, height and diameter, significant predictors of volume? What do we say?
Yes, because the p-values are less than,
You got it.
so you're just looking at the p on the tape, correct?
That's right.
Got it.
Yep, just looking at the tape, that right there. That's what the text typically uses is the alpha level is 0.05. It should say otherwise if it doesn't. I like to say, well, I think it should be explicit in the question. So the questions that I've written, I'm 99.5% sure that they're all explicit if it matters. If that makes sense. Because I think that's part of the process of laying out your hypothesis is saying at what level I'm willing to reject it. So, yeah. So keeping, okay. How much volume is expected from a tree that measures 79 feet tall and has a diameter of 11.3 inches? Okay. We have annotate. Minus 57.99 plus 0.34. That's height times 79 plus 4.71 times 11.3 equals 22.090. So, and then we're supposed to round to the nearest cubic foot. So 22 cubic feet. Okay. A tree in the data set measures 79 feet tall and has a diameter of 11.3 inches and is 24.2 cubic feet in volume. Determine whether the model gives an over or underestimate of the volume of this tree. So the same tree right here, 79 feet tall, 11.3 inches. On average, we're expecting 22 cubic feet. Under, yeah. Yep. That makes sense to everybody? Okay. Now, we have a multiple linear regression model. A multiple linear regression model was constructed to predict the cooling rate of a turbine given data on the number of drive shafts, motor RPMs, cycle pressure ratio, and inlet temperature, exhaust temperature, and airflow. The regression output is below. Okay. Select all the predictor variables that would be included in the constructing the next regression model in the iteration. Okay, so they're saying, yeah. Second, third, you know. I think that's what they're going to say too. They're saying airflow as well. airflow, extemperature, intemp, RPM, and chefs. They're saying everything except CP ratio. Is that what I'm seeing right?
Yeah.
Because it's got a huge. Now, how they came up with this, I honestly don't know. I mean, right. I think if you're cutting out, if you're having a cutoff on your alpha, I would say, okay, you have a cutoff on your alpha, but this is one of the reasons we do the homework together. Yeah, I'm presuming that's it. That's not an alpha we've worked with. We've worked with 0.05. We've worked with 0.1. I'm guessing that they're saying that it has slightly better performance than chance, and that it has 50, but I'm honestly at a loss on why they chose that one. So I'm sorry. If you want me to dig, I can, but it's not again, as far as the exam, as far as the final exam goes, that's not something I'm going to be doing, because I don't think you should be I don't think you should be removing variables in the first place. If CP ratio is important as a social scientist, you leave CP ratio. If all you're trying to do is predict, that's a different story. But don't always agree. But all right, so that's the homework.